Good morning, good afternoon, good evening, wherever you guys are in the world. Hello, welcome. Hi, Joshua. You're Jingbo, Joshua, right?
Yes, I am. I go by both.
Nice to meet you.
Nice to meet you.
All right. So people are starting to trickle in now. We'll start our session in a bit. Yeah, feel free to type in the chat where you are in the world and what time zone you're in, morning, afternoon, evening. We're in Montreal, Canada, so it's the morning, 10:30. Okay. We'd also like to kindly ask all of you to please mute yourself during the session, and we'll have a designated Q&A session at the end where you'll be able to ask questions. And if you haven't joined our Discord channel, please check your emails. I'm sure that our executive administrator, Miriam, have sent out that information for you to join as well. Okay, it's 10:32. Let's get started. So please, Sebastian and Farhad and Hossein, Najeeb, if you see more people coming in, please submit them. But it's time to start now.
Okay, Eugene, are you going to do you have any other announcements, or should I?
Yeah. Oh, sorry. I guess we didn't explain that clearly. We usually do a bit of an announcement, introduce our mentors, and then you can start right after that in 5 minutes or so. Does that sound okay? Okay. Perfect. Awesome. Okay. Welcome everyone to the first session, the first official session of McMedHacks 2022. Previously, we've gone through 3 weeks of preparatory Python programming classes prior to the opening ceremony yesterday. So today will be the first. I am so sorry. Prior to today's first official session that will be instructed by Dr. Najeeb Khan. And the topic of today will be Introduction to Classical Machine Learning. All right, as always, welcome. And first off, we would like to do a land acknowledgement. So if you do not know what land you're on, I invite you to click on this link. The slides will be shared later to know which land you reside on. Our virtual event is based in Montreal, Quebec, which is the traditional territory of Kanakahaka, and is on land which has long served as a site of meeting and exchange among indigenous peoples, including the Haudenosaunee and Anishinaabe nations. We acknowledge and thank the diverse indigenous peoples whose presence marks this territory on which peoples of the world now gather. We encourage you to learn and discuss about the history of the land on which you reside, which you can click on this link for. As always, for communication, you can send us an email, medhacks2021@gmail.com, our founding year, and further instructions can be found on our website. And there's always reminder and conclusion emails before and after each session sent by Miriam. And rules for the participants: please treat your fellow participants with respect. Use your real name on Zoom. One thing that I would like to emphasize is that you please log on to your Zoom for every session with the same email address, so that we can track your attendance. And please log in. Please make sure that you actually log into the Zoom account in order to join this. And please remain muted during presentations, workshops, unless it's designated Q&A time. Ask questions in the Zoom chat or the Discord channel. You can direct that directly to our mentors or the instructors. If you attended our opening ceremony yesterday, you might have seen this timeline shown yesterday as well. The official program started yesterday, June 11th, which is the opening ceremony, which will go until August 6th, which is an 8-week program. And currently we're at week 1, which is Introduction to Classical Machine Learning. And as I mentioned before, there will be 1 or more workshops per week. This week, we're at this point. Please check our website, go to Program 2022, and under work. So opening ceremony was yesterday, and under workshop today, we're here at June 12th, and we'll have 2 additional workshops for this week that will take place on Wednesday and Friday. The one today will be Introduction to Classical Machine Learning. The one on Wednesday will be Classical Machine Learning, a case study in XGBoost. And last but not the least, on Friday, Sebastian and I will go through the Introduction to Image Processing, Image I/O, and Image Transformations. As we also mentioned yesterday, if you didn't attend, the program structure will be consisted of usually a seminar that's happening on Saturday, and workshops 1 or more. The time for seminar and workshop will always be at 10:30 a.m. Eastern Daylight Time. The mentor tutorials that Hossein manages, the time and date will vary during the week. Mentors are responsible for creating the assignments. Some of you were asking whether we'll have any real-life examples to apply things to. Please go ahead and check out the assignment. That's where you find those materials in. Offline help will be on Discord and via email. And now it is my pleasure to introduce our mentors of the week. We have Joshua Tian and Benjamin Weiser. So Joshua is a PhD student at McGill. He specializes in applying machine learning techniques to transportation problems. Joshua, please go ahead and unmute yourself and introduce yourself if you would like.
Hello. Hi, good to meet you, everyone. So I'm a PhD student at McGill. And so what I'm doing is basically to study the traffic network system. And that's a complex system that will throw out a lot of data, and we apply machine learning techniques to study the data, find patterns, and try to predict things. And all these insights we get from this practice will be used by both policymakers and urban planners, or maybe just drivers. And we have people in our group studying different things, ranging from drivers' behavior to the high-level aggregated dynamic system patterns.
Wonderful. Thank you very much for joining us, Joshua. And Benjamin, are you here?
Yeah, I'm right here.
Hi, nice to meet you. Would you like to introduce yourself as well?
Yeah, I'm Ben. I'm a master's student at McGill as well. And yeah, I'm doing AI or machine learning for chemical purposes, such as protein and drug interactions. Trying to get a machine learning model to be able to predict what is the best drug for a certain protein, basically, so that we can basically develop drugs in a new way. And yeah, super excited to be here. Thank you.
Perfect. Thank you very much. We are very much looking forward to working with you both. Announcements, I guess old announcement, but new announcement for people joining for the first time. Every time after the session, we'll send out a conclusion email with a YouTube unlisted playlist link that will always be the same. So whenever the session is recorded, we'll upload it to the YouTube list, and then this YouTube playlist will be shared with all of you. And the presentation slides today, as well as our instructor's slide today, will be shared through Google Colabs that will be in a common Google Drive folder called McMehex 2022 for participants. And this will be updated every once in a while, but the link remained the same. And last but not the least, like I mentioned many times, the Discord channel. All right, so if you also didn't attend yesterday, we announced the attendance criteria / evaluation criteria yesterday. Many of you were asking whether you'll be rewarded with a certificate of completion. Yes, there will be one. And how we'll calculate that is based on the Zoom email address that you have right now, which is why we kept emphasizing, please always log on with the same Zoom account, and please log into the Zoom account. That's how we'll track it. So 70% of the workshop attendance and 50% of seminar attendance will be necessary for you to get the certificate. If you cannot make it in person because of the vast time differences that we have here, Hossein and the mentors have worked out a quiz, a post-workshop quiz, where the video of the workshop / seminar will be embedded into the quiz, and you can answer the quiz to make up for that attendance. But we do 100% welcome and encourage you to attend live as well. Yes, and everything will be recorded. Great, and now it is my absolute pleasure to introduce our instructor of today, Dr. Najeeb Khan. Dr. Najeeb Khan is an adjunct professor with the Department of Electrical and Computer Engineering at the University of British Columbia. His research at UBC involves machine learning techniques for brain-computer interfaces, specifically for speech production. Prior to UBC, he completed his PhD at the University of Saskatchewan, Canada, working on regularization and interface acceleration techniques for deep neural networks. Dr. Khan also serves as a senior data scientist at Global Relay, a provider of compliant archiving, messaging, and e-discovery solutions for highly regulated industries. At GR, he is working on voice analytics solutions, including speech-to-text, keyword search, and speaker identification. He is driving the efforts to scale these models to process millions of minutes of audios monthly. From 2018 to 2021, Dr. Khan was with Calian Advanced Technologies, a space communications company, as a machine learning lead. He led Calian's efforts to simulate mega constellations for efficient radio resource management in satellite communications. So thank you very much, Dr. Khan, for coordinating with Sebastian and our team and making this the workshop currently a reality. Thank you very much. So I'll leave the stage to you. Please go ahead and start sharing your screen.
Thank you. I'm hoping you can see my screen.
Yeah.
Yes.
All right. Thanks for the introduction, and thanks everyone for joining in today. I'm really excited about this this talk, and yeah, looking forward to any questions as well. Before I start, you might have access to the Colab. I recommend you can open it and follow along. There are sort of coding exercises there, which I will be performing, but those are provided to you already. So you don't need to type anything. You could just watch me code them in. So that's a little bit of that. One more thing on the logistics is here, whatever I code is for simplicity and sort of really for understanding. So if you have learned much more sort of more Pythonic or more cryptic ways of doing things efficiently, this is an introductory sort of lecture. So things might be a little simple in here. So with that, let me get started. So here's the outline. One more thing about the Colab and this this thing that I'm presenting is they are equivalent. So your collab and what I'm presenting here would have the same contents. So here's an outline. I'll briefly define machine learning, what are the types of machine learning, and what common tasks could be solved with machine learning. Then the most important part is, if you get the gist of what machine learning is, then the main part is what are the components of a machine learning algorithm. So any traditional machine learning algorithm would have three components. There is a model, there is an objective to achieve, and then there is a learning algorithm that basically picks the model. So those are the gist of the talk. And in this component, I will be sort of gradually helping you to understand each of the component and maybe do a simple implementation of each of the stage. And then we will use what we developed in the components section to do a toy example of diabetes progression prediction. So that's the sort of the principled and theoretical part of the talk. And then at the later part, I will introduce you to the scikit-learn library and some of the more machine learning related concepts that you need to apply to the problems. At any point, if you have questions, type them in, and periodically I will go back to the chat and sort of answer the questions. So with that, let's get started. So what is machine learning? So it's the study of algorithms that rely on a collection of examples of some phenomena. So what is an algorithm? It's just a procedure. If you are in a hospital, you admit patients and then they line up in queue. There is a process to perform each task at each step. So that's what an algorithm is basically step-by-step procedure to accomplish a task. And so machine learning is the study of algorithms that rely on a collection of examples. So the steps will be sort of computed by the algorithm itself. You just need to provide it examples of some phenomena. And the defining characteristic of these algorithms is that they should improve their performance with experience. So if there is anything or any algorithm that you come across, and if you give it 100 examples and it has poor performance, and then if you give it 1,000 examples, then its performance improves, then basically you are working with machine learning algorithms. It is not pure search. So if you have a box of balls and you want to find which ball is red in color, you can search all the balls, look at one at a time, and then once you find the red ball, basically you have learned nothing in this process. So search could use machine learning, but pure search is not basically a machine learning problem. Similarly, planning, if you make a schedule for yourself and if you don't learn from that schedule, if you just do it mathematically, then that's not machine learning. And reasoning, again, could use machine learning, but in general, pure reasoning is not machine learning. So I mentioned these because ML, machine learning, and AI is the broader field, which include all these search, planning, reasoning. Machine learning is a subfield of AI. So to make this distinction that usually, because machine learning is so pervasive in all the problems now, like search also uses machine learning, planning also uses machine learning. But sometimes then you learn the buzzwords and the boundary becomes blurry. So that's good to know that purely these fields are not basically distinct from machine learning. Okay, so let's look into the types of machine learning. So the first sort of type of machine learning is supervised learning, where you have a bunch of examples, pairs, x1, y1, x2, y2, and so on. Each one is an example or a data point, and the whole thing is called a sample or a data set. So what could be an example of this data set? Say you have images and you have labels for that. So image one, let's say, contains images of tumors, and you want to know whether it's a malignant tumor or it's a benign tumor. So we could have a data set of these images where like for X represents the image and Y represents the label, whether it's malignant or benign. In general, X is known as a feature vector and Y is the target or label. So this is the data set. And if we have something like this, if we have labeled examples, then the field of algorithms or machine learning algorithms that we will be dealing with is supervised learning. So what would be another type of learning mechanism is basically semi-supervised learning, where you have a bunch of examples as before with labels, but a lot more examples without labels. So for example, you have 1,000 images for which there is the label is available as either malignant or benign, but you have, let's say, 1,000,000 images of tumors that just are not labeled. So to basically take advantage of this data, you would use techniques in semi-supervised learning. The third category is self-supervised learning. So basically, you have only images that doesn't contain any labels, or that are not labeled at all. So there are two ways to deal with such data. One would be unsupervised learning, and the other one is self-supervised learning. So here we are talking about self-supervised learning. So in this case, we become clever and somehow find the supervised signal or the label for the data. So the main idea of self-supervised learning is to somehow find how we can label this data. So one simple example of finding a label for this data is, let's say we have this example image 1 and image 1 again, and if these two images are the same, then predict true, and if they are not the same, then predict false, right? So even though we don't know about image 1 and we don't know about image 2 and image 3, but what we can do is we can compare image 1 with image 1 itself, or image 1 with any other image, and that way we can generate labels. So this is good for basically learning good feature vectors. So that's just a brief intro to self-supervised learning. And the final and very common or popular method after supervised learning is unsupervised learning. So where we don't have labels at all, and we don't try to create labels. And it's where we just are interested in finding patterns in the data. For example, like if we have a data set of, let's say, patients, so we want to find out two clusters in these patients data set. One is, let's say, those who will recover from a disease, and the others who wouldn't, or one cluster that would sort of have markedly different characteristics from the other. So if you want to find two distinct patterns in the data, we would use something like clustering. Similarly, other applications of unsupervised learning is outlier detection. So if you have a bunch of samples, x1 to xn, and then you have a new sample xn plus 1, and you want to know whether this xn plus 1 sample is very much similar to the rest of the data or not, then you can use unsupervised learning to figure that out. Let me see if there are any questions. Okay, so other than these categories, is there are a whole bunch of other learning types as well, such as reinforcement learning, active learning, transfer learning, continual learning. And you put any word in there and search Google Scholar, and you will find a paper on that kind of learning. So it's just giving you a breadth of breadth of the fields of machine learning. Okay, so what are some of the common tasks that are solved by machine learning? So here is a list of just the very common tasks that are solved by machine learning. In terms of supervised learning, we have classification. We will look into this: regression, recognition or detection, segmentation, time series modeling. And then for unsupervised learning, again, we have clustering, dimensionality reduction, and outlier detection that we looked into previously. So let's look into classification. So what is classification? So in classification, basically the input could be the same across all tasks, but classification tasks are basically defined in terms of what we are predicting. So in classification, the target vector comprises of a finite set. So when you are predicting a category, let's say inputs are images and you want to predict the category is benign or malignant. So that's basically your target label is just two categories. And that's where you would use classification. If you have just only two categories in your target, then the problem is known as binary classification. And if you have multiple categories, more than two categories, and then the problem is known as multivariate classification. Moving on to regression. So in regression tasks, the target vector is continuous valued. So when you are predicting a quantity, let's say you are predicting a price or predicting other values that are continuous value that can take on any value in a range, that's where you are working with regression problems. So just as an example, the input is an image of a person, let's say, and the target is the body temperature, or maybe predicting the height or things like that, which can take continuous values. Okay, recognition and detection. So if you have images and it contains objects, so in classification, you would say whether it contains object 1 or object 2 or object 3. In recognition or detection, what you need to do is detect what object is in there and where it is located in the image. So that's sort of a more advanced version of classification and regression, because you have to specify the bounding boxes of each object. Similarly, segmentation is another really good example of a common machine learning task. So you have images and you want to figure out what region of pixels belong to the same object. So in here, the lungs are sort of shown in green, segmented out of the plain image. And finally, time series forecasting is another example of supervised learning, where you have a time series of data. So on the x-axis we have time, and on the y-axis we have this example contains the cumulative confirmed COVID cases. And so at each point, the machine learning model basically tries to predict what would be the count of the cumulative cases in the next time window. And it's sort of a regression problem, but sort of a different application of it. Okay, so going to examples of unsupervised learning. So let's say we have this data set with two features, feature 1 and feature 2, and we have samples from different sources that contains these feature 1 and feature 2, but we don't have any labels for it. So clustering can find the distinct categories in these samples. So here it's just two features, so we can visually see that this is one sort of cluster, this is another one, and so on. But in high dimensional problems, you cannot figure this out easily. So clustering could be used to sort of find out what are the distinct categories or clusters in this data. Okay, so now those were just some of the common types and tasks. There is a lot of ways to sort of categorize these types, and the lines are blurry, and many people have sort of different opinions, but understand that this is an introductory talk, and so what I presented is sort of a first order truth or first order categorization that would be easy to understand for someone that's starting out with machine learning. Okay, so now moving on to components of an ML algorithm. So this is also again a very narrow view of the models or the machine learning algorithms that we are describing here. There may be other models that doesn't conform, or ML algorithms that doesn't conform to this structure. So if you know a lot more about other models, please bear with me, because this is sort of an introduction. So going to the components, model, objective function, and learning algorithm. So the first thing is model. So we, in any ML system or algorithm, what we do is select the class of models that we are going to use. So this could be a neural network, or decision trees, or some sort of a model that contains some parameters. We will look into models in the coming slides. And then the learning algorithm basically picks one model at a time, or in parallel, that doesn't matter. But it picks a model that is, it chooses one model from the class of models. So the class of model contains, like, let's say, all humans, and then it picks one human out of the whole class. And then it evaluates how good is this particular model with these parameters. And to evaluate that, there needs to be an objective function. And that objective function is basically telling the learning algorithm whether the model it picked is good or bad, or how good it is. And based on this information, the learning algorithm can either select a different model, or once it is tired of selecting too many models and asking the objective function for so long, and it can't find another better one, then it just outputs this model and saying, this is the best model I have found it so far. So this sort of is the overall structure of an ML algorithm. In the subsequent slides, we will be looking into different models, learning algorithm, and objective function. So what are these models? So it's just nothing more than a function. So it relates inputs to the output. And the most simple model you could think of is linear regression. So in linear regression, what you have is you have these x1 to xn, slight abuse of the notation, where I had x1 as vectors in the previous slides, but now here it's just a scalar value, and x as a whole is a vector. So we have x1, x2, xn, and these w are the model parameters. Usually x0 is assumed to be 1. So this is just one specific model. You could come up with your own model, but statisticians have done analysis, and this is what there's a lot of theory behind it. As to why we multiply these two vectors, where x is the input and w are the model parameters. And so if you have examples of, let's say, x's like inputs, and let's say the target value is the average of that vector. Let's say if you have 1, 2, 2, and 1 is the input, then the average value would be 1.5. So if the targets are the average of the inputs, then what would be the linear regression model? So it would be something like this. The weights would be 0.25, 0.25, 0.25, and you would multiply the input, and that would give you the average value of that vector that's input there. So simple enough. So let's do an activity. Let's implement the linear regression model. So hopefully everyone understands functions in Python if you have attended the previous meetings. But if not, it's just this is what we have here is a function, and we have an input vector x and the weights. And we need to calculate the output and just return the output. So how would we do that? So we would just iterate over the inputs. So for input x in, or let's say calculate the length of the weights. So how many weights we have? So it's n equal to the number of weights. And then we would run a for loop. So for I in range n. So this would execute n times. And then we will take the input x, and you would get the first component of the input vector, and you would multiply it with the first component of the weights vector, right? And you would assign this to the output, but you want to add them all, right? Remember from the previous slide, we have W0 plus W1 times X1 plus. So to do that, we would do output plus input X times weights, or to be more compliant with the equation that we had previously. So you do this. Okay, so that's our linear regression model. So every time we get an input and the weights, this will compute the output of the model. So simple enough. That was linear regression. So what about other models? So what if we have a classification problem? In that case, what we would have is whatever we had for linear regression, but in classification, we want to predict either a 0 or a 1, like one class or the other. And to do that, we need to pass the linear regression output through another function called the sigmoid. And the sigmoid will basically compress the output in a range between 0 and 1. So what doesn't matter what the input is, maybe input is 1000, and in that case the output would be closer to 1, and if the input is minus 1000, then the output will be closer to 0. So these linear regression outputs are passed through this sigmoid function to basically transform it into a probability. So that probability is basically the probability of whether the output is a 0 or a 1. There's a question, what are the weights in here? So it's the same. These are parameters, scalar parameters that are learned through the learning algorithm. So currently we are just looking at the models. So once we define or introduce you to all the models, then we will look into the objective functions, and then we will look into how to learn the values of these weights. Okay, so that was a logistic regression. There are other models, such as a decision tree. So in a decision tree, you have an input X, and then it passes through different branches, and the output is basically the sum of all the branches. So how would this work? So let's say you have a blood test of, let's say, red blood count and white blood cells count. and you want to predict some disease, whether the patient hates some disease or not. So you could ask whether the white blood cells count is less than some threshold T1, and you could ask whether the red blood cells count is less than some threshold, and then based on the answer of those questions, you could decide the category. So this is the model. That's the model part. Why is part of the machine learning sort of set of model? That's the reason behind it is what should be the feature used in here versus in here. So you have red blood cell count and RBC count and white blood cell count. So which one should come here and which one should come here, and what should be these thresholds? So these sort of things could be learned as part of the learning process in these decision trees, and these could be extended to much higher dimension problems. I just explained a very sort of basic toy example. So the reason it's part of machine learning is because the structure is learned by the algorithm itself rather than providing manually these thresholds and features. Another model is support vector machine. So there are a bunch of models which are like motivated from different theories. In support vector machine, let's say you have two categories, the blue one and the green one. So the support vector machine basically finds a line that is basically in the middle of both the groups of samples, and the distance between the middle line and the positive or the negative example is basically, or the vector is basically known as the support vector. And so it's very similar to linear regression in form W times X, but the theory behind is or the principles and concepts behind it is quite different. So finally, neural networks. So they, in terms of models, you could just consider it as another model that relates input X to output Y. You will learn about this in the coming workshops, but just to give you an idea that in terms of models, these are sort of some of the models that you will encounter. Okay, so one final concept on the models is the model capacity. So what kind of input target mapping can each model represent, and what kind of decision boundaries can each model represent? So here's an example from some blog where the decision boundaries are plotted. So in here, we have a logistic regression model that we saw. So we have two sort of classes. One is represented by squares, and the other one is rectangles, triangles, and so there is a linear sort of separation between the two, and logistic regression can only do this linear sort of separation between these two. So if there is something more complex boundary required, like if you want to have more sort of finite control, then decision trees can get you arbitrary boundaries. So you could have these thresholds and find out the threshold for each example, and then this way you have almost an infinite sort of capacity to identify or sort of memorize each one of the examples. Of course, infinite memory is not good. So that's why you would in the next workshop you would learn something about XGBoost, and that's sort of a decision tree based model. Here, SVMs, the ones that I described in the previous slide, are basically linear. So they have a decision boundary similar to this one, but in here in this image, it's an extension of the SVM to nonlinear cases. And then for neural networks, they could do much more sort of complicated boundaries similar to decision trees, but continuous. Naive Bayes that we didn't look into in this presentation. So this just gives you some ideas on how the complexity of the model basically affects the data, the decision boundary. Okay, so those were models. So now you have a bunch of keywords in your bag as to what the models the model classes you can pick from. Now is the time to look into how to evaluate these models. Remember that we implemented one of the models, the linear regression model. Okay, so moving on to objective functions. So an objective function is a mechanism for the linear the learning algorithm to evaluate different models, and it is a function of both a data set and the model. So let's say we have given a class of models. So let's say all decision trees or all neural networks or all vector support vector machines. And so we pick one model out of it. So a model is basically having some parameters, and if we fix those parameters, then we get the specific model. And we are given a supervised data set with examples and labels. What an objective function, or it's also known as cost function or a loss function, does for us is it gives us an indication of how good is the model H on the ith example. So if I have this image, how good would be my predictions on this image, given that I know what the answer should be. So J represents the sort of the quality or the loss function or the cost of the prediction of the model on image I, given that I know the label of image I. And we have a data set, not just one example. So the objective function is a function of the whole data set and the model. And it basically combines or sums up all the costs of each example and then divides it by the number of examples. So that's your objective function. So for each type of problem, there would be a different sort of objective function. So for regression tasks, you would have mean squared error, and that's a very common objective function. For classification tasks, you have cross entropy, and there are a whole bunch of research areas to sort of investigate or develop objective functions for different problems. So let's look into mean squared error, which is primarily a regression used in regression tasks. So let's say we have an input xi and we have some quantity to predict yi. So we provide xi to our model h, and we predict some value for the yi. So let's say this was 10 and the model predicts 12. So a model that will produce the prediction closer to the target value would be a good model, right? In this case, we could just say, okay, find the difference, and that is our error. So if we do that, if we just subtract the predicted value from the target value, then that's just the error. But if the model always predicts higher value than the target value, then in that case, our error will always be negative and negative and negative. And if we want to minimize the error, then we will always, if this is predicting infinity, then this would be the lowest error that we can get. So that's not what we want. We want the value to be closer. So how about we square it? So we square the difference. So that seems reasonable. If we square it, then if it is closer, then if the target value is closer to the prediction, then we would have a smaller error. Otherwise, we will have a pretty high error. And as mentioned on the previous slide, we don't do it just only for one example. We need to do it for all the examples in the data set and average it. So if we do that, we have the mean squared error loss. So given this, a good activity is to just implement the mean squared error. So we have, again, a function, and we are past the target value and the predicted value of those particular targets. So these are in here vectors. So each component in this vector represent one example. So the way we would sort of solve this is we would again find the length of the vectors, so or the lists in this case. So we have the n is the length of the vector. Now for each of them, we need to calculate the error between them. So error would be the first example or the ith example target value minus the ith predicted examples value. So that's our error. And as we saw, that error itself is not very useful, so we need to figure out a squared error. So squared error would be error times error, and that's our squared error. But what we need to do is basically for each of these examples combine them together. So we would need to store the value in a variable, sum of squared errors equal to 0, and we will, for each one of these, we will add it to the, so this would be equal to squared error plus squared error. And in the end, what we have is the mean squared error, which is basically sum of squared errors divided by n. So this is basically how you would compute the cost function for this example. As mentioned earlier, these are already computed for you, so you could just analyze what you have there and run. Okay, so this was the model and the objective functions. We have covered a bunch of classes of the models, and we have looked at one objective function, the mean squared error. Now let's look into the learning algorithms. Again, there's a lot of complexity, but this is a very simplistic view of the whole machine learning system. So what an learning algorithm does is it ideally selects the model that minimizes the objective function. So we have seen the objective function j, which could be either mean squared error, which we computed or incremented, or it could be any other sort of model that's objective function that's out there. And what we need to do is we need to find the model parameters w that would basically minimize this objective function. So how do we achieve that? So before moving on to how do we achieve that, there is a very critical thing that I want to convey in here. So let's assume that we find this objective function, and then we minimize this, and we find out the weights in that basically minimizes the objective function. What we have achieved so far. So let's say we have n examples, and we find a model or weights of the model W star, and we observe a new input X. Can we guarantee anything about what this model will predict? And there is no guarantee, because past is no guarantee for the future until and unless we make some assumptions. So those assumptions are very critical to keep in mind all the time you apply the algorithms or machine learning to a new example. So those assumptions for supervised learning and the type of things that I described is basically that independent and identically distributed samples. So any sample in your data is going to be distributed according to some probability distribution, denoted here with a calligraphic D. And so if you have training data, or like the data that you have for training, if you have a new example, we assume that that new example would be distributed according to the same distribution according to which your training data was distributed. And the second assumption is that the samples in the data set are independent of each other. So if you have one image and another image, they should be independent of each other. It should not be like in a video frame where the next frame is dependent on the previous frame. So then in that case, there would be correlations, and the normal supervised learning and the optimization algorithms that we described here would have issues. So those are the sort of assumptions or limitations that are there inherent in this sort of analysis. Okay, so going back to the optimization problem. So we have the cost function, that is function of data set, and the parameters, and we want to find the best parameters. So the most common algorithm for this is basically the gradient descent algorithm, and it could be used for training linear regression, like logistic regression, SVMs, neural networks, what have you. XGBoost is basically again a traditional model that's uses gradients to optimize or find the models out of the class of models. So what it is, what is gradient descent? So let's say, let me try to annotate it here. So let's say we are somewhere here on this hill or mountain, and let's say this is our target position, because this is the J, the lowest value of J is a function of D and W, and W is in here is the location. So what would be, if you find yourself in there and you want to reach at this to this point, what would be the best way to get here? So you don't want to go uphill, right? Like that would be not very wise. You also don't want to go sideways. So if you go that way, you are not making any progress. And again, you don't want to go this way, because you are not getting closer. You are not getting closer in terms of the cost of J. What you want to do is find the direction in which the slope is decreasing the most. So that would be this direction, and you want to walk in that direction. Let me change the color. So you want to go downhill in this direction and take a step there and keep going until you reach the destination like this. So at each step, you are basically looking, where is the steepest direction I can go downhill, and then you walk that way. Of course, if you take two big jumps, you could also do that, and you would get somewhere here, and then you would want to go back and get it stuck in this loop. So what I just described here, it's a very naive view of this, but almost all optimization algorithms based on gradient descent are basically following this sort of mechanism. Okay, so doing, what does it mean in terms of mathematics? So in terms of mathematics, what we need to do is find the direction of the steepest ascent or descent, basically find the slope. And the slope is basically represented in mathematics by the derivative of a function. So all we need to do is find the derivative of our cost function with respect to the weights, and then just walk our weights in that direction. So if we have we start at some initial position that could be random, and then at each time step, we basically take a step in the negative direction of the derivative of the cost function. And that gives us our new weights. So this is the basic idea behind gradient descent. There's nothing more to it complicated for a beginner to know about it. The important thing is this mu, which is the step size or the jump size in the mountain example, and it's the step size in this learning. So as I described in the previous mountain example, if we take two small jumps or steps, then it would take a very long time to reach the target position. And if we take two larger steps, then we would be sort of jumping back and forth. So generally, this learning rate in these optimization algorithms is quite significant. Okay, so now a quick sort of recap. We have the model. We already coded this in the previous examples. We have the mean squared error. We also looked into this and coded this up. Now the final ingredient that we need is the gradient of J. And I've computed it, and here basically the gradient of this formula with respect to W. So you don't need to sort of follow through, but if you don't have a background in this, but assume that this is the correct formula at the bottom. So we have the 2m is the number of examples, h of x is the model prediction, yi is the actual or the target label, and target value, and xi is the input. So again, let's implement this. So I will try to do that in here. So we have x is the input matrix, y the target vectors, and weights is the weights of the model. So in this case, we have the model is basically a linear regression model. So first I would find out the length of the input, how many examples we have, and then I will figure out what the model predictions are for each of the input. So for each of the input, I would do linear regression model. That's the model that we described previously. It takes in the input, so let's give it the ith input, and it also takes in the weights that are passed. So this is just one example, but we want to do it for all the examples. So for I in range m, and what we need to do is keep track of each of the outputs. So model predictions would be a list. So we would initialize it as a list, and then for each of the prediction, we will just add the prediction to the list. So model predictions dot append prediction. So those are our model predictions. If you look at the formula for the gradient, so we need to subtract the model output from the target value from the model output, and then multiply by the example. So for I in range m, what we need to do is the gradient would be equal to the model predictions. And let's do it for the ith example. So that would be y minus so here we have the ith prediction of the model. This is the target value of that prediction, and we need to multiply this by the input. So multiply by x of I. So basically here, what I'm doing is just implementing the formula that I showed in this previous slide. So we have model prediction minus the target value multiplied by x. And as you saw, there was a summation, so we would sum this for all the examples. So we would have gradient equal to gradient plus model predictions minus target value times the input. And finally, we need to multiply it by 2 and divide it by m according to data for more. And that should be our this should be our gradient of the mean squared error loss. Okay, so now we have all the ingredients for this linear regression model, but we need to do the final sort of gradient updates for the optimization to happen. So we have what we had before was the cost functions derivatives. So we have the part where, let me go back to the slides. Well, we have this part, and we have the weights, and now we need to update the weights based on these components. So how do we do that? Basically, we compute the gradient, so that would be gradient is equal to compute gradient. It would take in the training data, and it would take the target labels and the weights. So that would give us the weights. It would give us the gradient, and then we need to update the weights. So weights would be equal to, the new weights would be equal to the previous weights minus the learning rate, which is passed in as a parameter here, the learning rate times the gradient. So this is the total sort of the gradient descent method for the MSE cost, the mean squared error cost. There is in the chat there is a question about whether we can use the normal equation to or the least squares formula for finding the weights. Yeah, definitely it's another method to sort of derive the same thing, the same weights. But the gradient descent is because it's applied to nonlinear cases as well and works in the nonlinear settings as well, or at least it's applied to all the nonlinear problems that we solve these days, whereas the normal equation is only good for the linear case, which is the case in linear regression. So that's why I introduced this one to sort of provide a general framework, so that in the next workshops you have a better understanding of the basics of it. Okay, so now we have arrived at the problem where we have all the ingredients for the linear regression, and we need to sort of use it for a toy data set. So we are given a data set of 442 diabetes patients. The input vector consists of things like age, gender, body mass index, blood pressure, and 6 blood measurements. And the Y is disease progression 1 year after the measurement. So you take the measurements today, and then the data set contains the disease progression from the current time to 1 year later. The data set is already pre-processed, so because we want to just focus on the model, the objective function, and the learning algorithm, I already provided a method that I will skip over, but basically you have the train X and the train Y data sets or metrics and vectors that are already provided there. So how do we now use this to do the prediction? So first, let's look into some of the data. So train X, let's say I look into the first example in the data. So I need to execute the cell that was before it that I skipped. Okay. So here is age represented in some normalized form and so on, and then there's a 1 for the Bayes term. If you go back all the way to the linear regression equation, then you would find that W0 is not multiplied with anything, so it's multiplied with a 1. So it's usually it's in the beginning, but it doesn't matter. And looking at the Y, the target value. So the target value, I assume, is the percentage, some sort of a percentage of progression between the time when the measurements were taken and 1 year later. So given this, now we have all the components to implement a predictor for this data. So what we can do is we can initialize a weight vector. So we need to find the dimension of the data. It is train X of 0. So that would be how many features are in the data. And then we need to initialize some weights equal to the dimension of the data. So we could just initialize everything with 0. So we could, if you are not familiar with this notation, it's a list, and if you multiply a list by d times, it would contain d zeros. So that's one way to initialize it with zeros, but for numerical stability and some complications of the stochastic gradient descent, it's generally better to initialize these with random weights. So I'll keep it with zeros for now, but in the example I provided, I initialized them with random weights. And then we just need to run the gradient descent on this. So we have, let's say, 20 iterations, and we need to update the weights based on gradient descent. We provided with the training inputs and the training outputs and the current weights. So this, if we run this, this would basically train the weights and give us the I think the function name is perform gradient descent. So this would run the gradient descent 20 times and update the weights 20 times. Of course, we need to sort of do more plotting and analyze what the weights look like. But let's say that procedure is successful. In that case, how would we do? Let's say I have this train X example, let's say example 7, and I want to do the prediction for this. So what would I do? I would just use the linear regression model with these new weights. So linear regression model train X, and I need to pass in the weights of the updated weights to this model. It's training, and the result for this example is predicted to be 148. So let's look into what the results look like for let's look into what the result looked like for the sample 7. So what is the Y label for? It's 63. So we see that it's very far off on this example. Let's try another value. Let's say look at sample 9. So it's again a bit off. So let's use random weights, random, and let's use for each of the weights, let's use a random value. So for I in range D, let's append random dot random. So each time we call this random, it will generate a random value between 0 and 1, I suppose. Okay, so it's, yeah, so it's not the perfect model, but training further probably it would convert to a better solution. Okay, so this basically gives you some of the nitty-gritty details of what simple model, how would you implement a simple linear regression model, and what are the components, and they are basically common to most of the sort of algorithms that you would see. I'm hoping everyone is familiar with plotting, but if you are not, if you have two lists, you can use Matplot's library to do the plotting. So I'll be using this next. So I just wanted to digress in here. Okay, so let me look at before moving on to the next section. Let me take a look at the time. So could someone confirm at what location time? How much time do we?
Yeah, we still have 13, 15 minutes. We're good. You're good.
Okay.
So
Cool.
11:47. Yeah.
Okay. I'm in a different time zone, so it's at 47 for me. So hard to.
Right. Yeah. Still 13, 15 minutes is fine.
Okay. So looking into so we have so far covered what it works from the inside and how like each component works, but in practice you don't want to implement all this stuff, right? Like you just want something to use quickly, and a lot of people have built so many libraries. One of them is the scikit-learn library, which has all the functions that are common in sort of traditional machine learning. And here is a really nice cheat sheet of the sort of problems that you could come across and use scikit-learn for that. So if we look into here in the regression portion, this SGD regressor, so we basically implemented a gradient descent regressor in here. But there are other methods as well. If we do like lasso regression or SVR, support vector regression. So this library contains pre-built sort of methods where it's really simple to just call a function and produce an output. And so all these previous slides are basically a little bit of a theory as to what's happening in the background, but if you have a problem, you could use the scikit-learn library, and now you would have a better understanding as to what is happening in each step that you make a decision when you select a cost function, or when you select a model, and so on. So there are regression tasks that are solved with these models. There are classification, so support vector classifiers, naive Bayes. Logistic regression is also in there, and which we will look into in a bit. And then dimensionality reduction problems and clustering. So the k-means clustering is a very popular algorithm or model for clustering. Okay, so the sklearn or scikit-learn library contains a bunch of data sets to play with. So here I'm just using a digits data set. So what does it have is basically it has a data set of handwritten digits. So basically arrays which contains pixels of the digits. So the way to load it is basically you import the datasets module, and then there are different data sets. The documentation is given for each of the data set on the website. And so it's really simple to just get your X and Y and not worry about any pre-processing. It's already processed for you. So you get the examples and the targets for them. So just printing the length of these X and Y. So there are 1797 examples, and you could plot them. So previously I showed you something like this, but it wouldn't be very useful. So for example, if we plot the first image, then it's just 64 length values, a vector or list, and it contains values that are varying between 0 and 14, but it's not very useful. But as we know, this is digits, so we could transform it into a 2D matrix into a shape of 8 times 8, and then use the pyplot I'm sure method to sort of show it. So as you see, this input 13 or example 13 contains probably a 3 as I can see it. So this is just a basic sort of data set loading and how would you do visualization. Fitting a model is really simple. So in the previous example, we did linear regression and all sorts of like math and implementation. Here it's really simple. So you import your model. So from sklearn, you would pick your model, whether it's S3M, support vector machine, or linear models like logistic regression and linear regression, or you would say, I don't know if neural networks are there in sklearn, but if they are there, then there would be a neural modules that you could import from. And in here, I'm importing a logistic regression model. So that's the model. It will contain, it would be equivalent to the linear regression model that we implemented the function. This is very similar to what we had there. And then we basically instantiate this model. So if you have looked into if you have attended the previous workshop on object-oriented programming, or just generally know, this is how to instantiate a logistic regression classifier model. I should rename this to a regressor because this is not a classifier, and we fit this regressor. So the way training is done is basically calling a fit function on this regressor and passing it the training inputs and the training targets. And if we do that, it just does all the magic. In previous case, I was doing 2,000 or 5,000 in here by myself, running the loop, but here you just specify how many times you need to perform this gradient descent step. And so if we run this, we will have a regressor that is well trained. Next, we would pick the 100th example. So we will just randomly pick, let's say I equal to 100, and I is basically my example number, and I would pass it to the I would pass it to the regressor to predict this this example for me and print it. So here it's training. The logistic regression is training in here, and so it predicted the line. This line printed this array of 4, so it predicted that the output is 4, and the image is also 4. So you see, this one is like much more. The accuracy is much more better than the linear regression that we implemented ourselves. That's because we just saw the basic bare minimum of everything, right? So there are a bunch of things, best practices, all sorts of like little techniques and tricks that are implemented by people in this logistic regression sort of model, or like any model that's in scikit-learn. And also we loaded the data using the data set. So the data set is already pre-processed. So it's always good to understand using a simple example, but always use a standard library when you are working with real projects. Okay, so we fit a model. We fit a model. Sorry, what was? Okay, so there is a question, why not use predict xi? It's because the prediction works on batches, so it expects a list of. So you could do something like this, where we pass in a list. The predict method basically requires a list to be passed to. Okay, performance evaluation. So we have fit the regressor to this data, but how do we know how good is our model? So that's where accuracy or different metrics comes into play. So accuracy is basically the correctly classified examples divided by the number of all examples. Nothing surprising there. So if you have n examples and by 2 are classified correctly, then your accuracy is 50%. Okay, so we don't even need to implement this metric. So in scikit-learn, you have the accuracy score already coded. So you could predict your outputs and using your regressor, and then you can just score it. What was the name that I gave it? Okay, so here it is saying the accuracy is 1.0. So it's a 100% correct model. So is that correct? It doesn't sound good, because whenever you have like this 100% accuracy, it's not usually achievable in practice. So how does it come to be 100%? So did our model cheat? So that's the question, and probably it did, because in this example, what we did was we trained the classifier with the training data, and then we use the same data to basically find the accuracy. So we asked it a question, like the classifier had already seen the question first. Think of this as like you are a student and you have an exam tomorrow, and you already saw the exam, what questions will be there in the exam, and then later on someone asks you to sort of write the exam. Then in that case, it's really easy because you could memorize, so you could have 100% accuracy. So how do we deal with that situation? So in that case, we can't just use training data to evaluate the model. We need to divide our data into a training set, a validation set, and someone else would evaluate this model based on like some test data, or the real world will basically evaluate this based on the test data. So the training set could be 80%, let's say, of the data. This could be validation set could be 10%, and test set could be another 10%. And we will use the training set for the optimization and fitting the model. And the validation set will be used for things like which model class to select, or which optimization methods to use, or which learning rate to use. So based on the validation set performance, we will tune that number. And once we are all done with our development, then test set performance is what we will report to the external stakeholders that, hey, this is the test set performance for this model. Okay, so how do we do splitting using scikit-learn? So again, the model selection module contains a method called train test split, where you pass in the inputs and the targets, and you specify how much should be your split. So if the training size you want to be 85%, then you would say the test size is 0.15, which is 15%, and it will return four sets to you, or one matrix and a target vector, and another matrix and a target vector. So if we evaluate this, we see that the training set is now about 1500, and the validation set is about 270. Okay, so looking now, training the classifier on the training set, and then doing the evaluation on the evaluation set. Let's see what the accuracy is like. So we have here an accuracy of 0.95 and not 1.0 exactly. Okay, so coming to the metric part, where we had accuracy as a measure to evaluate the classifier. So this is a really good toy sort of metric to use. But in real life problems, data is usually unevenly divided into classes. So we usually have more tumors than benign tumors than malignant ones, or we have more sort of legitimate transactions than fraudulent ones. So to deal with that case, we have other metrics like precision, recall, and accuracy. I assume we are pretty short on time, so I will skip these for a second and just go to the evaluation part of these.
Najeeb, it's okay. We can go till 12:30, including Q&A. So I think if you want to talk a little bit more about these evaluation metrics, go ahead as well.
Okay. We have half an hour, like 20.
Yeah, technically, but okay. that includes Q&A.
Okay, cool. Okay, so looking into these other metrics, so coming back to the uneven or imbalanced data. So in accuracy, let's say all your transactions, like let's say you have the problem of tumors, let's say. So you might have, let's say, out of 100, only 2 malignant ones, and if your model always predicts that the tumor is benign, then the accuracy would be 98% because the data set is imbalanced. So to deal with this case, we have other accuracy metrics or other metrics for evaluating the performance, and some of them are listed here. So precision. So when you have high precision, that means you will have low false positives. So if you have a problem where false positive is very expensive, let's say you have a patient and you are if you find a disease, you are going to do an invasive sort of treatment to the patient, and that invasive treatment is going to be potentially harmful to the patient. in that case, you want really high precision for your classifier because you can't, like, you don't want any false positives, right? On the other side is the recall. Like, it's okay if you give some pills to the patient, but if you miss the positive case that you say it's falsely negative, the patient has some sort of disease, and you miss the disease, then in that case, false positives would be very detrimental, and so you want very high recall so that you have low false negatives. In most cases, you want both to be in balance as well. So you want precision to be high and recall to be high. You don't want this imbalance that one is high and the other is low. So to do that, you could use something called F1 score, which is basically an average of the precision and recall. And F1 score would be low if these two are not in balance, and it would be high if these two are in balance and closer to 1 in accuracy as previously. So to do all these metrics, you could use again sklearn's matrix library, and the precision recall, F score, and support method basically can give you all these quantities fairly easily. So here, I'm printing out the F1 score per class. So there are 10 classes in our example, and for each class it printed what is the F1 score of the class. Okay, did I miss something? Okay, so finally, feature engineering. Okay, finally coming to feature engineering. So given a data set that consists of X and Y pairs, X is basically called a feature vector, which contains these different quantities, and Y is the target label. And so feature engineering is the process of converting these raw data into useful feature vectors. So the main problem in here is that you could have like a lot of raw data, and then what do you use to feed into your model? What features do you want to use or select for the model? And that's the domain of feature engineering. So in the diabetes example that we saw previously, we had age, gender, body mass index, and so on were our sort of features. But think about it, as a raw data, there was height and weight and other many different sort of raw data. But the builders of this data set basically chose the body mass index because that's more informative than just using the height or the weight of a person. So those sort of things where like the input variable is much more informative and correlated with the target is useful. So there are a few caveats. I'll go through this fairly quickly. So so far we have seen that the features could be numerical values like 1, 2, 3 or 0.1, 0.2. But how do you deal with categories? Like, let's say you have colors as input, so like red, green, blue. So then how do you input this into your model? So to do that, you would basically one-hot encode it. So if you have 3 colors, red, green, and blue, you would replace the string red with 100, the green with 010, and the blue with 001. So encoding this example input into this one-hot encoding, we would have red replaced with 100. Okay, many times we need to standardize our input in the range of 0 and 1, or -1 and 1. So if you remember from the if we remember, so there's a question, could we replace the color with a single numerical element? You can do that for cases where there is an order. So if you have like bad, bad, and then good and best. So if there is like an ordering in the categories, then you can do 0, 1, 2. But if there is no ordering, then you are just misleading your model, because colors don't have an ordering. Red, green, blue is the same as like green, blue, red. So they just misleads the model a little bit if you do just numerical wording. Okay, so coming back to the normalization part. So many times you have values ranging in different ranges. So for example, this first scalar value might be in the thousands, and the next one might be in the millimeters, like very small values. For the optimization to work, it's usually better to standardize all the features between 0 or 1, or -1 and 1. And so here is a way to basically normalize. You subtract the mean, and then you divide by the mix in the mean. So how do you do that with like the examples that we saw previously? So let's say we have this logistic regression. If you just run it for a few iterations, it says it's not able to converge. So the reason is because the data is not normalized. So how do we normalize in this scalar? And the way we do it is basically import a standard scalar sort of object, and then fit it to the training data, and then transform the data, the training data, with this preprocessor. And this way we have now X scaled, and we can use that to basically train our classifier, and hopefully this time we don't see this error and it converges. So this is the benefit of using standardized values. So now let's what happens if you standardize? What happens to the evaluation? So let's just, for simplicity, let's print the accuracy. So the accuracy is still sort of the same. Let me not use the scaled values. Let's use the so let me go back one step. Okay, so here we trained the model, and here we found the validation accuracy to be dropped from like 95 to 71, and that's because we are not normalizing it the validation time. And so if you train with normalized data, then if you train with normalized data, then when you are predicting, you should also predict with the normalized or scaled data. And if you predict with the scaled data, then the accuracy is fine. One last thing about missing features. So sometimes you would have examples which contain missing informations. For example, for someone, the age and the average blood pressure or some other quantity would be available, but the body mass index may be missing. So then there are ways to sort of either replace it with an average value, or remove this row from the data set. And finally, for classical sort of machine learning, this is a very important concept of underfitting and overfitting. So sometimes you would see that that you have a model that predict well the labels of the data it was trained on, and other times it would not be able to. So our linear regression example, like we saw, the accuracy on the training data was really poor, and that indicates that it's an underfitting problem. So high training loss or poor performance on the training data is basically known as underfitting. And the reason is that your model is too simple. So linear regression was very simple model for the or the features that you basically picked for this model are not informative enough. So to mitigate underfitting, you go to a complex model or you pick the informative features. So you either do model sort of change or you do iterations of the feature engine. On the flip side, overfitting is where the model predicts really well on the training data, but poorly the data from validation and test set. So that's a symptom of basically overfitting, where you have a large difference between the training and the validation. And that is basically due to either your model is too complex. So later on, when you train huge neural networks, you would find that the training data works really well, but on validation, and even in the logistic regression example, we saw that on training data, the accuracy was 100%, but on validation, it was 97. So it's not exactly overfitting because 97 is still a very good value, but if it was like 50 or 60, then that would have been a case of overfitting. And another cause other than the model would be too many features and very few examples. So here is a link to a tutorial on scikit-learn, and if you want to use it for your practice. Useful resources as a starting point, I think the 100-page machine learning book is really good for someone starting, because it's just 100 pages, so you don't need to sort of spend too much time. And during these machine learning course on Coursera is really good. So that's all that I had. I hope you enjoyed, and I will take any questions.
Perfect. Thank you so much, Najeeb. That was very pedagogical. I enjoyed it very much. So if anyone has any questions, please raise your hand and feel free to start asking. And then after that, our mentor chair, Hussein, will announce the dates and time for this week's tutorial. If there's no questions, I saw there was a very active chat going on during the lecture. If you have any more questions, please go on Discord and we'll mentor. Oh, there is a question. How do I, Johnny?
Yes, Johnny, that's correct.
Okay.
Thank you. And thank you for the great talk. When you tested on your training in all the data, you had like accuracy of like perfect accuracy. But sometimes I test on my training data and I have bad performance. So say 60% in 2 classes. So what does it mean when you have that? I mean, and is it common to test on your training data, or you should not do that?
That should be the first step to do. And that basically is the slide. So that means it's underfitting. Your model is underfitting. So the inability of the model to predict well on the labels of the data it was trained on. So if you have a training set, you train the model, and then you use the training data to sort of evaluate the model. And if it is not doing well on your training data, so there could be a bunch of reasons, but one of the main, or like apart from the random reasons, the principal reason is that it's underfitting. Your model is underfitting to the training data. So how would you mitigate it? You either go to a different model that's more complex. So if you are just using linear regression or logistic regression for classification, you basically would use you would want to use a more complex model. If a more complex model is beyond the reach, then what you need to do is like do more feature engineering, so that the problem becomes simple for the logistic regression. So if you had just only image, like let's say you are doing speech recognition and you only had speech data, then you want to add another modality, maybe like also facial expressions, and that might improve the performance. So sort of adding more features would help with that. Does that answer your question?
Yes, thank you so much.
Oh, I would like to add something here. Sometimes, if possible, this is unfortunately it's not possible always. Adding more data, collecting more data would be helpful. It helps with giving your model more really clue. Also, it helps the model to not overfit. But as I mentioned, it's not always possible. So a question came up, actually a couple of questions I can highlight since it might be beneficial for everyone. One was regarding people with background in the medical side. The content might be a little bit difficult to grasp in 90 minutes. So what is your suggestion for those audience?
Yes, so yeah, definitely 90 minutes is difficult, but as I mentioned, the resources are mentioned in here. So either picking up the book or the course to sort of go through that. The other one is to just run through these examples. So scikit-learn has a bunch of examples on linear regression, logistic regression, classification. So that's where I would point to sort of run a few examples yourself. The other thing is that you don't need to grasp all of it. It's just good to sort of have some terminology in your mind when you are working with things. Of course, what you bring to this is basically your domain knowledge and expertise that are more critical. And as you work with simple problems and understand this, you would be able to ask the right questions, like apply this machine learning to the right problems. So that's where I see the most value where you could sort of given that you know what problems could be solved, mapping that to the problems that you already have. So perhaps you might have more to add to that.
Absolutely, I completely agree. People coming from medical side, if you have really that terminology that you can translate and be a connection between AI engineer, machine learning engineers and medical side, that would be really valuable. The skill that honestly is even now is rare. So you don't need to be a complete machine learning engineer, but understanding the concept would help you. For example, if you are working with someone, they come up with a model that is underperforming, you should know both underfitting, overfitting, and how really to guide that person and ask for change or update in the model to get a better result. Besides, machine learning in general is a highly in demand skill, both in academia and industry. And one reason is that it is not something that you can take a 1 hour or 2 hours to learn. This means that it requires work and takes time. This is why we don't have a single lecture or a couple of workshops. We have 8 weeks program because we hope that during this time you have a chance to come to the session workshops, learn. There are gaps. You need to identify those gaps and study on your own for filling that gaps. Ask your question from the mentors in the tutorial session, as well as being engaged in the Discord channel. So that would hopefully provide the environment which you can learn better.
Do we want to take some more questions from the chat?
Sure.
I mean, we can, if there's a question that hasn't been answered, definitely we can go. Otherwise, feel free to unmute and ask your question as well. It might be easier to.
Yeah, and just before that, Hossein, would you like to tell everyone about this week's tutorial?
Sure. It's going to be on Tuesday from 12:30 to 1:30 p.m. And it's going to be on the same Zoom link. And our mentors, Ben Weiser and Joshua, will be there to answer you guys' questions on the assignment. So please take some time to go through the assignments that we will provide soon. like with the summary email after the workshop, and come to the questions on Tuesdays. Come with your questions on Tuesdays. Okay.
Awesome. If there's more questions, just please go ahead, unmute.
Sure, quick question. I think I missed the memo about this, but how will the assignments be evaluated and submitted?
Yeah, so there's going to be no grading to the assignment, but we do have the tutorial. So you just need to do the assignment and then come to the tutorials and ask any questions that you might have. And the main evaluation / attendance criteria that we have is what was presented at the very beginning, which is 70% of the workshop and 50% of the seminar, which is why you need to log into the Zoom account with the same account every time, so that we can track attendance that way.
Thank you.
In general, assignment is for self-evaluation and also an opportunity to practice what you learn and go to the tutorial with those questions and get engaged in the learning practice. I see one question from the chat. I think it's a good one to go through. How to select, in general, it's how to select our features. Najeeb, do you wanna go through it?
Yeah, sure. So the first path is the feature should be informative or correlated with the target. So based on the domain knowledge, you should come up with the set of features that you think would predict. So for example, you can predict the data a computer is using based on like the MAC address. So predicting the direction of the car from the tire pressure. So that sort of features are not going to be helpful, right? So based on the domain knowledge, you should come up with, the domain expert should come up with what is correlated with the target that we are predicting. So that's the broader set. Once we have the broader set, then there are many ways. The empirical way is to just evaluate based on the validation set, which features are the most informative. That's one way, just very empirical. Then there is like more statistical ways of doing, like if you have a small number of features and you really want to select only a few specific ones, then the chi-square test and all sorts of statistics is there to evaluate each individual feature at a time and see whether this improved the performance or decreased it. But I would say in the sort of models that you would be using, I think the empirical way of evaluating the model with different set of features is one way. The other one is like in deep learning that you will study in these future workshops. You just use the raw data and don't do as much of feature engineering. In the traditional cases, that's also the case with something called regularization and the lasso regression that we just glossed over in the scikit-learn example, where it just does the feature selection for you, where it just damps down the weights of those features that are not really important. So there are these different approaches, but the empirical one sounds like a reasonable one. I'm sure others have better ideas on this as well.
I completely agree. If you have domain expertise, definitely use that to collect features. Having too many features is not always a good thing, and this is why we do feature selection. There are, as Najeeb suggested, there are a lot of methods, statistical approach to learn which set of features are good. I shared a link under, so it's under scikit-learn package. There are feature selection approach. I highly recommend you to go take a look at them. It is this question really a good approach, a good style of learning. You come with a question and you ask community. Here we try to really build that community. In general, if even after this school, you can post this question on Stack Overflow. It's a really good and active environment. First, of course, search if there is some similar question asked by someone else and perhaps answered. And in many cases, that should be the case. If you didn't find any similar question, just go and ask your question. Another thing that also was suggested for deep learning models, the whole really power of deep learning approaches is to learn the best set of features. So that's the difference between traditional machine learning or conventional machine learning with deep learning. In deep learning, we try to learn the best feature representation from the data. In that case, you don't need to, in most cases, you do not need to have this feature selection unless you have a model that have several inputs. For example, imaging plus clinical data. In that case, you might do some feature selection for the clinical part and then merge these features down the road. But we will learn a lot about deep learning approach in the future sessions.
Thank you so much, Farhad. If there's no more questions, let's see, we're perfectly on time, 12:30. Thank you very much, everyone, for coming today. And thank you so much, Dr. Khan, for your wonderful lecture today. And we look forward to working with you in the future again. Great.
Thank you so much. Yeah, it was great questions. Thanks for this.
Yeah, I hope you enjoy teaching as well. Great. So that's it, and everything will be posted on the YouTube channel, and Miriam will send out a conclusion email again. Thank you.
Thank you so much, Najeeb. Bye-bye.
Thank you, and bye, everyone.
Bye.
Thank you, Najeeb.